So before we do this last example, you might like to read there's an example in your textbook about minimizing the expense of building a cylindrical aluminum can, something like that. So it's this problem that we're going to do is sort of a variation on that one. So if you like, you can kind of see the problem that comes in between. This one is actually from the problem set at the end of the section, and we can answer this one too, I promise. So you saw some, yeah, if I was going to guess, something like that last problem we did is probably how you're going to see optimization on the AP test. So here about the calorie burning, when is the rate the greatest? If you see an optimization problem on the multiple choice section, the one like we did about the acceleration, that's pretty common. That would be pretty standard. This one that we're about to do, this is the one it's kicked up like another notch, because we're going to have this problem that you've seen before. When we go to write our equation for the quantity that we want to optimize, we're going to find the easiest way to write it, the way to write it that kind of makes sense to us, is going to contain two variables. So we're going to have this problem where we're going to have to stop, figure out how to rewrite that equation in one variable, and then the rest of the steps are pretty straightforward. So here we go. Problem. You're going to design a right circular cylindrical can. So soda can. It has a rectangle that you fold around in a circle to make the sides, and it has a circle for the bottom and a circle for the top. But this time, we're saying when we decide how expensive this can is going to be to make, we can't imagine that we're going to reuse the scraps from cutting out the circles on the tops. We're going to cut those circles out from squares that have side length 2r on a side. So here, let's read the whole thing. We're designing a 1,000 cubic centimeter right circular cylindrical can whose manufacturer will take waste into account. When we cut the side, which the side of the can is a rectangle that you fold around, so there's no waste when we make the side. But when we cut out the top and the bottom, which are circles, they're going to have radius r, and we're going to have to use a square of material that has a measure of 2r on a side. So if you have a 2r by 2r square and you cut out a circle that has radius r from that, you're going to have those little corner pieces that are waste. We're going to just have to throw those away. So imagine those are pieces of aluminum. The total amount of aluminum used up by the can is going to be, this A is for surface area, or the area of the aluminum that we're using, 8r squared plus 2 pi rh. So now we have our question, what is the ratio of H to R for the most economical can? And that's our sign here. We need a sign every time that we're having an optimization problem in here. This is most economical. You could say cheapest. Just knowing that the thing that costs money in this operation is the material for building the can. So it's not about how many rivets it takes or how much you have to pay the workers. It's about how much aluminum actually gets used up. Remember, some of it's getting wasted too when we make a can. So step one, what is it that I am trying to optimize? Do I need the maximum or the minimum? And step two, can I write an equation, an expression for that quantity in one variable? All right, so I'm writing up my steps here. Again, that part's optional. We're gonna have to do these things. I'm just sort of writing it up in a nice order so that you can compare it against those steps and kind of get the flow. We want to minimize the total area of the aluminum. So that's an important idea. These minimize or maximize costs, they're kind of a common problem. So you just need to know that that means that you want to minimize or maximize the amount of material used. And here, it's kind of nice. What is A? I don't know. Maybe A is 8r squared plus 2 pi rh. I'll give you a little funny face because, hey, they gave it to us, right? Can't be wrong. So we do, in fact, have an expression for how much area of aluminum is going to get used up by this can. The problem is that's 2 pi rh. That was a little funny, my h there. Let's fix him. But this doesn't meet the requirement. The requirement is that we need an equation for a that uses only one variable. Now, whether it's r or h doesn't make a difference, but we're going to have to pick one and try to write the whole equation without using the other variable, the leftover variable. So the thing that we have that can help us, this is sort of where the work in this problem comes, is we know that 1,000 cubic centimeters is the size of our can. We have to understand, though, what is that? That's the volume. So the volume is 1,000. And what's another expression for volume? That's pi r squared h. For a right circular cylinder, this formula is going to come up all second semester, so it's a good one to have memorized now. If you didn't know it now, that's fine, but we're going to need to know a formula for the volume of a cylinder. Pi times the square of the radius of the base times the height of the can. So pi r squared h. I can isolate the h in this equation, and then whatever I have on the other side of the equal sign is going to be an expression I can use in the place of h in this formula. So I'm going to divide both sides by pi r squared, and I'm going to have that 1,000 over pi r squared equals h. Now I can finish step 2, which is a is going to equal 8r squared plus 2 pi r times 1,000 over pi r squared. I know I'm going to have to take the derivative pretty soon, the derivative of a, so I'm going to simplify this expression just because it is going to make the next step of taking the derivative easier. So a, in its rewritten form, simplified form, 8r squared plus, that's going to be 2,000 over, the pi's are going to cancel, that's nice. One of the r's is going to cancel. I'm going to have 2,000 over r. So can I write an expression for a in one variable? Yes. A is equal to 8r squared plus 2,000 divided by r. All right, so I know that when I go to make my table, I'm going to have inputs that are r values and that are endpoints and critical points of a. And my outputs are going to be a values because I want to pick the r value that gives me the smallest area. So in order to find those critical points, I'm going to need to know when the derivative of a prime, equals 0 or is undefined. So here it's my turn to find a prime. This is not so bad. That's 16r with a new exponent of 1. And this is here plus 2,000 divided by r. That's the same thing. Feel free to do this a couple of different ways. 2,000 divided by r is the same as 2,000 r to the negative 1. So when I take the derivative, I like to use the exponent like here to rewrite with the negative exponent so I can use the power rule. So this is going to be minus 2,000 r to the negative 2. The minus sign is from the negative 1 coming to the front to multiply, and then the 2,000 and then the negative 2 exponent is from decreasing the exponent on r by 1. All right, well that's not so bad. This function is undefined for the value r equals 0. So you might ask yourself, do I need to use r equals 0 as a critical point? Does it need to go into my list of input values when I make my table? So I'm going to argue that no, because if you actually had a radius of 0, you couldn't make a 1,000 cubic centimeter can, right? So no matter how long your height is, you can't have a radius of 0 and have any volume at all to your can. So I'm going to say that the only critical points that we're going to put into our table that doesn't include 0, or they're going to come from letting this expression, 16r minus 2,000 r to the negative 2, equals 0. So I think I told you, I'll admit to you, I don't actually memorize those steps and use them out in, I don't remember which number is which step, but I'm pretty sure step 4 is I'm supposed to solve a prime equal to 0. Something like that. So I want 16r minus 2,000 At this point, you might like to write that as 2,000 over r squared to equal 0. Now, the way to solve this equation without accidentally dividing by 0 or accidentally multiplying by 0 is to rewrite it so that there is a common denominator. So I'm going to try to get a denominator of r squared for both of these terms. So I'm going to imagine multiplying top and bottom of this first fraction by r squared. So here's what I end up with. See if you get the same thing. I end up 16r cubed minus 2,000 over r squared equals 0. So that's a fraction. I have an equation where I have a fraction equal to 0. This expression, this equation, no, the expression on the left-hand side of the equation is going to be undefined when r is 0, but we already talked about that. So the solution is going to come from when the numerator equals 0. That's when 16r cubed minus 2,000 equals 0. So it's the same as saying 16r cubed equals 2,000. 16r cubed equals 2,000, which if I divide both sides by 16, I get 125 here, which means r is going to equal 5. All right, so I haven't quite answered their question yet, but I want to stop at this moment and say that we have a critical point. That's great. We found a solution of a prime equals 0, so we're going to have to go back and make that chart. But before we do that, hold on one second. Just to get us excited, I have graphed the a function that we wrote, the one variable a function. So a equals 8r squared plus 2,000 over r. And I would just like to point out that if you, this is r across the horizontal axis and area up the vertical axis, check out the place where r equals 5. I do in fact have my minimum area. That's the lowest down point on this graph. That's going to be our correct location of the absolute minimum. So if you wanted to use a grapher to check that you're on the right track before you finish doing out a bunch of algebra or calculus. Good strategy. All right, so my next step, I'm pretty sure it's step 5, is I'm supposed to make a table here of all the input values that are endpoints and critical points of the function that I care to optimize. I said I cared to optimize area when I have r. Do I have any endpoints? Could I imagine an endpoint? I certainly can't use negative r values. Is 0 an endpoint? I think we decided that 0 can't be an endpoint because if I had a 0 radius can, I can't have 1,000 cubic centimeter volume. So 0 is not even in the domain, so it can't be an endpoint. I have a critical point when r is 5. And do I have an endpoint on the other end? Is there anything that stops me from making the radius super big? Of course, I'll have to make the height super small. Hold on. All right, I stopped and thought about that. I could essentially try to make h 0 to get a second endpoint, but again, I'm going to have that problem where I can't actually let the height equal 0 because I'll never get any volume. So I end up kind of like that other problem we did with just one input value in my table, and that is where r equals 5. I could compute the surface area, but let's ask ourselves, did they actually ask for it? The question here, what is the ratio of h to r for the most economical can? We could find it. Let's see. A is going to equal 8 times 5 squared plus 2 pi times 5 times, I'm going to have to stop and figure out what the height is that makes h. What is the height that makes the radius 5 that still keeps my can at a volume of 1,000? So I need, because I was trying to put the right h value here. So what is it? 1,000 equals pi times 5 squared times h. That was an equal sign. So I have 1,000 equals 25 pi times h. I'm going to have 1,000. Oh, I knew this already, that h is 1,000 over pi r squared over 25. I'm having trouble writing 25 today. 25 pi. So that's what's going to go here. 1,000 divided by 25 pi. This is going to, I could compute this expression to get that minimum area. Turns out they didn't actually ask for it. What they have asked for is for me to write the ratio of h to r. This is h. Notice this. It'd be very nice if I simplified this, right? How many times does 25 go into 1,000? Well, 25 goes into 100 4 times, so this is going to be 40 over pi. So if you're checking in the back of the book, you'd like to get the answer that matches the back of the book, they've asked us to write a ratio of h to r. So ratio is a big fraction, right? So of h, so 40 over pi, to r we said was 5. And that simplifies to 8 over pi, or I think the back of the book actually writes it out as a ratio with the word 8 over pi to 1. I'm totally happy with this answer. I'm totally happy with the answer 8 over pi. The back of the book writes it out as 8 over pi to 1.